waiting for people to log on.
All right, I would go ahead and get started, Jerry.
Okay, well, welcome everybody. I welcome you all to this because as I near my complete retirement here, I decided it's time to share things with other teachers and other educators. And I've had such a wonderful career and so many wonderful opportunities, and so many people have helped me out over the years so much that I wanted to be able to give back in some way some of the things I've gained, whether it be knowledge or materials or so on. And now that I've retired from Lewis and Clark officially, and I'm not teaching even past retirement when I was teaching the summer geology program, I decided I might as well start sharing what I have with other teachers. So I've set up this workshop for the summer, August 5th, 6th, and 7th. And in this workshop, I will share, methods and practices I've used over the years, both even with elementary and middle school and high school students and grad students, to teach geology in a hands-on way and showing, where we use teamwork to investigate and learn the rocks. It'll be a 3-day intense session. And at the end of the session, the participants will walk away with handouts, materials, rocks, both student sample sets of igneous, metamorphic, and sedimentary, as well as some rocks to have on display in their classroom, and perhaps even some mystery rocks that they can use for investigating and asking questions and exploring beyond what we do in the regular class, just with identification and an emphasis on the rocks telling a story and telling us about where they came from and something about the earth we live in, so that the rocks themselves are not taught just as things to learn, they're taught as things to extend to the world around them. And so that's my goal. I'm looking at having at this session a minimum of 9 teachers and a maximum of 12, just so I have enough resources for everyone to take home with them. And then if I have more resources, I'll open it up later for more people to come and get help and assistance and maybe take home several hundred pounds of rock. I have lots, trust me. In fact, the program at Lewis and Clark, I always taught on my back deck here. We called it Lewis and Clark South because I had better rocks than the college did. So, and most of the rocks that people receive have come from the Pacific Northwest. These are rocks that I've collected myself. So anyway, if you got a good hefty back and you like rocks and you like kids, I encourage people to apply for this. I am setting a priority of elementary and middle school simply because often those teachers don't have the resources that the secondary teachers have available, or sometimes the budgets they have available. And especially elementary, where they have to teach so many different subjects, there's often not enough money in the budgets for the kind of resources to get geology samples. So anyway, that was why I said that. But everyone's welcome to apply. And I'm hoping to get people who are really interested in teaching geology, would like to gain a foundation in it, as well as some hands-on samples to have for their classroom. That's what this is about. So this show today will be sort of a buffet of the kinds of things they'll get during the summer at this summer session. So it's not a geology class as such, but it's sort of a picture of where we're going in this class. So
you could also call it a networking, a collegial networking thing too. Yes.
Yes, that would work as well. Yes. So I'm going to ask that the applications, which will come through us today, we'll talk about this later, where I've asked that they're due June 20th. Okay. And that way I have time, people have time to get the applications in, and then I can let the people know right away who's accepted for this special 3-day session. And again, if I have materials left over, I'll open it up, probably announce it through OSTA again, and invite people to come and get lots of and share rock samples to take home with them. Okay, well, I guess, Lori, if we're Ready? Let's go to number one. I sort of set up a recipe for rocks. Dealing with middle school and elementary students, and even high school students, even grad students for that amount, sometimes they get a little confused. And so a recipe for rocks, you choose your ingredients. Minerals, they're just pure substances. They can be elements or compounds. Choose the amount, add to the rock, and then basically we have three geo appliances in your home. You can bake it in a magma chamber. Be sure to melt all the ingredients before cooling. Select a cooling rate, and it has to be fast or slow, and that'll give you different rocks. Or if you don't want to use the magma chamber, take stuff from weathered rocks and allow the separated minerals to settle, or if in solution, precipitate them. And the other thing you can do is place in a tectonic plate press and allow heat and pressure to alter ingredients. But if you go to the third method, the tectonics, do not melt. That's our important thing with this recipe. So these are the three major areas, the way we produce rocks made from minerals. And of course, then we come to, these are the places they're made. Let's see in the next one. Participants of this class, this is to give you an example of what we're going to be doing. We'll be using field identification for this class. And field identification is necessary because that's easier for people to handle. And all field identification, remember, is a best educated guess until you get rocks back to the lab. So basically, this would be, for instance, on the screen right here, would be a set of the igneous rocks they will get. They're going to get about 13 igneous rocks in the set, but this shows you the basic 6. On the upper left is rhyolite. To the right of that is andesite. And to the right of that, the dark one over there is basalt. And then you notice below we have a granite on the lower left, and then a diorite in the middle, and a gabbro on the right. What we're going to do with these rocks, and this is what we'll do with the students, is to show them that they are organized by composition, going left to right. The ones on the left are higher in silica and lower in iron. As you go to the right, they get higher in iron and lower in silica. This is important because the more iron it has in it, usually the darker the rock. And also, the more iron, the easier it flows, and the less silica, the easier it flows. So the ones on the left are sort of as lava. The top ones would come out as lava. They would be kind of sticky. And then the right one, basalt, flows very easily, at least, at least for lava. And the middle one, of course, andesite, is in an intermediate. But those 3 top rocks come from lava. Of course, they are called extrusive, and they cool fast. So the other, in addition to composition, we'll be looking at particle size. And if you look down from the rhyolite on the left side, down to that granite, you'll notice the particles are larger, and you can see them with the naked eye. That's because they cool in the magma chamber. They cool slower, they cool beneath the surface of the earth, and the particles have time to find one another, the minerals, and so they get bigger and grow bigger. And so rhyolite and granite are exactly the same composition, they just cool at different rates. If we go over to andesite, it cools slowly to form diorite, and if we go to basalt over here, it cools slowly to form gabbro. So basically, on field identification, we can tell whether these were formed from a lava flow or if they cooled underground, and that'll tell us something about the geology and the stories that have to go on. Every rock has a story to tell, and it's interesting because the rock tells us something about the geology we're looking at and the landscape we're looking at, and yet the landscape in turn tells a story about the rocks we'll find there. So it's kind of a two-way street. If any of you ever remember an author by the name of Burt Baylor, Burt Baylor wrote a very interesting book called Everybody Needs a Rock. She's a Caldecott author winner, and her books are excellent. And rocks are sort of special. I think it's important that students and teachers alike actually touch the rocks and feel the rocks, because there's something, you make a connection with them. And if you haven't read Everybody Needs a Rock, it's a great story. It's good for adults too. Most of us have our favorite rocks anyway. Okay, Lori. The magma chamber. It's an interesting place. And this is called the Bowen series. He was a a scientist, Canadian, I believe, and he decided to start cooking these things to see how they changed. And he put in the things that were in rocks, and he found a very interesting thing. As he melted all these things and allowed them to cool and checked on it, he found that each of these things started changing into what it was. For instance, if you go to the upper left, look at olivine. Olivine is very high temperature. Its gemstone of olivine would be called peridot, for any of you August birthstone people. But it is a single chain silicate. But if it cools down, it becomes a double chain silicate, and you get a black pyroxene and so on. So it turns out that as the temperature dropped, each of these minerals began to change into something else. And this would be happening in, we think, magma chambers. And finally, if you get down to the very bottom, everything came out to potassium, muscovite, and quartz. Now we know quartz, sometimes we refer to quartz type systems as silica. Quartz is silicon dioxide. The question is, well, where was that silicon dioxide that comes out at the bottom? Well, it was up there because most of these compounds near the top were in fact silicates. They were the complexes connected to the irons, the magnesiums or calciums. And finally, when it gets cool enough, the quartz separates itself out. The interesting thing about this is, on the right side, you see it says types of magma. Well, if we were to take a lava at very high temperature with the feldspar from the right and the iron magnesium compounds on the left and stop the magma at this high temperature, that comes out as basalt. That's the mafic. If we stop the temperature at the intermediate level, the elements across come out as a mixture, and that forms andesite as the lava. And if we go to the bottom where it says felsic, remember in elementary school, we're often taught granite's made of quartz, feldspar, and mica. Well, there those three are right there. That comes out as rhyolite, okay? Now, there's one other interesting thing about the Bowen series. The Bowen series not only tells us about how lavas and magmas form different rocks, but they also tell us something about the stability of them, the durability of them. Notice olivine, pyroxene up here at the top. It is stable under high temperatures. It's not stable as the temperature drops. And so we go down to quartz here. Quartz is stable at a low temperature. So this means that when these come out on the surface of the Earth, quartz should be much more stable than the olivine pyroxene type things. And in fact, if I go to the next slide. Oh, I'm sorry. Well, this is my fault. Just remember those two things we talked about, durability. We'll just remember that these two at the top, these two together, pyroxene and olivine, make something called peridotite, which is mantle rock, okay? And down here we have quartz. Just remember those two things and where they are. Okay, let's go to the type of volcanoes these produce. The basalt, the ones at the top, the basalt lavas, flow very easily, and we get shield volcanoes. They just spread out a long ways, like the Hawaiian volcanoes and Newberry volcano in near Bend. The composite volcanoes, andesite mainly, but also you get some basalt and rhyolite. They're called composite because you get different things. It's a stickier lava. It can build up higher, and we get the very high mountains like the Cascade volcanoes and the Andes volcanoes. And of course, andesite, the main kind of extrusive lava there, is named after the Andes Mountains. Okay, and the next one, Lori, please. Cinder cones. These are usually basaltic. They're usually found near other volcanoes. Two very famous ones in Oregon, if you go to the Bend area, are Black Butte on the way over from if you've traveled the Mount Hood Highway or the Sisters Highway over, and Lava Butte just south of Bend, part of the National Monument there. Calderas usually occur because of explosions. Now, they could be because the magma disappears, or they could be because water flows in and you have a steam explosion, but often they're done because rhyolite is so sticky, it sometimes plugs up vents and things and explodes. And as it vents. And common rhyolite eruptions would be Crater Lake, which is really a caldera, as you know. Newberry Crater, which is a caldera. Now, even though it is a basaltic shield volcano, it has a major element in there of rhyolite, the Paulina Peak, and then a huge obsidian flow, which is rhyolitic with the pumice down there. And of course, perhaps the most dangerous volcano in the world is caldera, Yellowstone. And it's, of course, Yellowstone was made from the light-colored yellow rhyolite that is visible very much in the Grand Canyon of the Yellowstone there. And the next one, Lori. Okay, weathering and stability. This is what I was going to talk about. I love this slide Lori provided and this slide together because they show something. Remember, we talked about how granite is those three: quartz, feldspar, and mica. Well, when you have weathered granites, and this is a slide of, this is granite here, and look at all the debris coming down from it as the granite breaks down. Well, the most stable part of that breaking down granite is going to be quartz. And if you look over here at a scene we might see in Oregon on the ocean, we have a beautiful sandy beach there. The question is, how did we get the sandy beach? And the sand is made up mainly of quartz. Here's the connection. Most of our sandy beaches come from the breakdown of granites on our continent. And so water not only helps break them down, it's also the transport that helps get them to the sea. And then the ocean currents, as the sand comes out of large rivers like the Columbia and so on, gets washed by side currents and parallel currents into the coves and areas, and we get our sandy beaches. So it's an interesting connection. So weathering and the breakdown of all these things and the stability of them can be predicted. So remember we talked about back in that Bowen slide, the very top that had the olivine and pyroxene that makes a rock called peridotite, which is basically mantle rock. If mantle rock comes to the surface, it rusts very fast because the iron in it is very unstable. And if you go down south of Grants Pass, you'll see huge masses of this orange hillsides and rocks. And that's just mantle rock that's been pushed up, and it's basically rusting away as the iron breaks down. Okay, next slide, Lori. Thank you.
Yep.
And sedimentary rocks. We need weathering. They need to break down. They can be formed by precipitation, with gypsum and some of those things, and salt, or they can come down and look at the sandstones layers. They can come down and we get clastic. They finally build up enough weight that they hook together, okay, and basically become sedimentary rocks. And the next one, please. And of course, it could be debris from organic material. For instance, cherts are often made from the siliceous organisms in the body. And then we have the limestones, and a lot of fossils are basically the skeletal remains. And of course, deposition of a lot of plant material with chemical alteration to reduce it so it's just in carbon, gives us coal and things like that. One other kind of precipitation I want to mention, though, is our state rock, the thunder eggs. Basically, silica or silicon dioxide is not very soluble, and yet this sticky lava that we talked about, rhyolites high in silica, it can form bubbles, and those bubbles hold. And if water gets in there over thousands and thousands of years, the tiny amount of silica that's left in it can be left behind, and it fills up and makes a geode or a thunder egg, as we call the solid ones here in Oregon. It's also how we get petrified wood. So there's actually precipitation of silica going on as well to produce these. And so fossils become a major part of our understanding of geology, and especially helping us figure out a timeline when radioactive isotopes aren't available. Next one, please. Okay, metamorphic rocks. I love these because they are really interesting. And it's really fun to look at metamorphic rocks. Minerals are changed by heat or pressure or solution process or any combination of those. And they're associated usually with, and we basically have mechanisms for them. The first one down here on the left would be a contact metamorphic rock. Contact just means, for instance, an igneous intrusion, maybe a piece of a magma chamber or a vent or a dike comes up, and it basically heats up the rock, the country rock it comes through. So if it's coming up through the crust, it heats up the rock around it. And so what happens is right next to the magma of the igneous intrusion, you get a high level of metamorphic change, and it decreases as you work your way out into so-called what we call country rock. And so you can actually get zones around it of different kinds, 3 or 4 different kinds surrounding it. For instance, if it were to intrude on an old seacoast with lots of sand or sandstone in it, that sandstone can easily become quartzite, for instance. Now, over on the right, you see a continental plate moving to the left and an ocean plate moving to the right, and we get subduction there, which we'll talk about in the next slide. But you see that subduction, when it eventually melts, creates a magma chamber, and that magma chamber goes up, and that's where the contact metamorphism occurs. But the two plates pushing into each other form what's called a regional metamorphism, and we'll look at that in the next slide. Lori, thanks. Okay, on the right side is the regional, and you see the two pieces pushing together. And notice that the temperatures there, the Celsius temperatures increase as you go down. And as you go down, for instance, if we take the rock, for instance, let's say this was a shale up here, at around 100 degrees Celsius, it gets pressed with both the heat and pressure into slate, and then it goes to phyllite, goes to a schist, goes to a gneiss, the banded variety, and then to a migmatite, which is almost melted. A migmatite is really cool because you'll see the bands of a gneiss really get swirled and to the point of almost melting. Of course, if it melts, it's no longer a metamorphic rock. We go back into the igneous, part of the rock cycle here. Anyway, the participants this summer will get a full series of some of these metamorphic rocks, okay? A full series of them, of all different mechanisms. And the third mechanism is the subducting plate. Now, the subducting plate usually is an ocean plate because the basalt is more dense than the granites of the continent. And as it subducts, that ocean plate stays cool because it's associated with water. In fact, it takes water down with it sometimes bonded in complexes, but sometimes the water itself. And so the mechanism here is more pressure and lower temperature. Over here on regional, we had high temperatures, high pressures. Here we have basically high pressure but low temperature changes. And here the basalt changes into an intermediate metabasalt, and then it goes on to form something called blue schist. The interesting thing about this is, though, the water that it carries down starts changing the rock down here around it it's going through, and it brings back various changes. So the water can change gabbros, for instance, into serpentinite and things like that, serpentinite on into jade. But that same water it subducts, water lowers the melting point of the surrounding rocks. And that lowering of melting points means then we start to get melting and we get a magma, and magmas begin to rise, and hence we get a cascade range inland from the subducting plate. So, but anyway, metamorphic rocks, very interesting. And like I said, they'll get a full set of series this summer, there's people who come to this particular workshop. Next slide, please. So, stories to tell and questions to ask. How do we find ways to make all this meaningful for our students? Students love stories, and the more stories you can tell, the better. Everything from Wagner and his continental drift, bets in the and the Columbia Gorge discoveries of the floods, the Missoula floods. It's, perhaps we just start with our home, Oregon, the Pacific Northwest. How were they formed? It's important. Are there clues around us to help us understand? Maybe the Coast Range or the Cascade Mountains or the Columbia Gorge can help us. And on the right is a map showing the last of the Juan de Fuca plate segment going under and subducting off our coast. And of course, that is what has built up the Cascade Range as we know it. And that subduction has also folded and bent it into our Coast Range as well. And some very interesting connections with this. Anyway, it's very important that the students realize how magnificent an area we live in. Oregon, the whole Pacific Northwest is incredible. And of course, it allows us to talk in a reasonable way about earthquakes because they are going to be a part of this subduction process that we have to go through as our continent changes and as it adds on to it. Next slide, please, Lori. I have some fun questions. For fun for the students, they could be discussion, they could even initiate research. For instance, will Los Angeles be part of an island off the Oregon coast someday? Or why don't we find dinosaurs in Oregon? Or what state or province has the most Cascade volcanoes? Where's the deepest gorge in North America? How many of these do you know? Will the Oregon Coast Range be part of the Olympic Mountains someday? Where's the largest obsidian flow in North America? Why are the oceans of the world located where they are? I mean, we know they're there, but there's a reason they are where they are. It's kind of, and geology has a lot to do with that. Well, everything actually. What's the largest volcano in Oregon? Most people miss this one. Why doesn't Hawaii have beaches like those along the Oregon coast? What city may have the most volcanoes of any metropolitan area in the US and maybe in the entire world? How many of those do you know? How many of those do you want to know? Okay, next slide, Lori. Well, being a teacher for so many years, I had to give final exams, not that I always wanted to, but so here are my final exam questions for you, or maybe after you study geology or want to find out. Plate tectonic theory suggests that Mount Hood should sit about where Portland is. Why isn't it there? Second question. How is Oregon related to the Yellowstone hotspot? And that one is a really interesting one. And the ongoing research on that one is still going. In fact, I grew up fairly near Yellowstone. I grew up in Idaho. So when I started my teaching career over there, I was able to take my students on field trips to Yellowstone and Craters of the Moon and the Idaho sawtooths. So that was an interesting part of my education before I came to Oregon. Okay, next slide, please. Okay, so this has just been a buffet of kinds of things the teachers will encounter and explore this summer. They're going to leave with rocks and hands-on materials and ideas. They'll be given an opportunity to go beyond the 3-day session. So basically, I know it's summer, so I only planned this for 3 days. They'll be intense, but I'm going to volunteer my time for the next 3 days, the Thursday, Friday, and Saturday, for anyone on a volunteer basis. If they want to come in and learn more, they can. Possible fossils, paleontology, evolution, geology of the solar system, the evolution of the galaxy, mystery rocks, field trips. I have just had spine surgery, so I may not be able to go on any field trips, but I might at least have good field trip suggestions. More in-depth study of any topics we covered in the first 3 days, like more about the Pacific Northwest, earthquakes, plate tectonics, geochem, or brainstorming, anything they want to brainstorm, and give them a chance to try out some hands-on activities that they might want to take back to their classrooms. So just, there's 3 days added on. My time's available if anyone who participates in the summer is interested. Next slide, please.
I just added, just to FYI, I just added links to the paper copy of the application. It's a Google form. You're going to have to make a copy of it so you can see what kind of questions.
Oh, yeah, right. Okay, yeah.
And send them in to them. But then I've also included for those of you there the online application form, which is just a Google form, which has the same information as the paper copy. So you have options, and I'll be sending those out again in the follow-up email as well.
Oh, Laura, that's great. So we want teachers who will teach a geology or geology class next fall. You don't need any formal geology training. Like I'm going to give, this is my choice, I guess, but I would like to give priority applicants who will be teaching elementary and or middle school students and get those students really excited in this and give them some chance for some real hands-on things. There's no fee. Participants, you have to bring a sack of lunch each day. We're going to have a working lunch. We'll be on my back deck here. You'll have to provide some containers for your rock samples to take back to your class and folder or binder for all the handouts you will get. I'm asking people to purchase the book you see on the left, Reading the Rocks by Marcia Bjornerud, and read it by the first session. This book was written by Marcia. She teaches geology. She was several years ago selected as the Professor of the Year for the US. She's a very excellent writer and an interesting person. I was fortunate enough to be able to talk to her one time, and she's one of the most interesting people I've ever talked to. Applications through OSTA, and there is an application form. And the class location will be in Lake Oswego, it'll be at my home. The applicants who are accepted, I will give them specific directions and everything else, anything else they need.
Okay, just real quick, I'm having some people, the Google form copy of the application, you're going to have to make a copy of it. You don't have access to, because I didn't want people filling out the form there. And then for some reason we're having some problems with the online form, but
Online also?
I will
Okay.
work on that. Okay. So
Okay.
again, I'm gonna send y'all
Yeah.
follow-up emails after we're done here so that you can get all of that information. Okay.
Okay, yeah, fantastic. And I guess our next slide is the last one, maybe?
No.
Okay, I'd like to thank OSTA for helping with give out the information and the application process for this. And huge thanks to Lori. Oh man, she's been so incredible. And you cannot believe the technical problems we ran into today. So that's why she's advancing slides. But she's Lori, thank you. You're just worth your weight in gold. And I would like to ask all of you to spread the word to teachers that you know who will be teaching geology to apply for this, because I would love to really get some enthusiastic teachers here and start getting these materials out to classroom teachers so students can actually get their hands on these things.
Yeah.
Anyway,
By the way, you need to know that Jerry used to be he was one of the OSTA presidents back in the day.
Way back in the day, yeah. But anyway, I'm open to any questions if you want to, if there's time for that, Lori. It's up to you, though.
Absolutely, we got plenty of time. So if anybody has a question, go ahead and unmute yourself and have at.
Jerry, do you want more rocks to
Well, I'll tell you, if this goes well, oh, you got some more there. I love it. If you know what we might do is set up a repository here for supplying teachers. We might just come to that. But I have a shed with about 40 crates of rock. And so anyway, if this works well and other people want to sort of do the same thing, maybe we could set up a repository and where teachers can come and get what they need for their classrooms. Because when you buy these class sets of rocks for your classroom, these commercial sets, number one, you don't know where they came from. And two, they may look or not look like anything the students would see here in the Northwest anyway. And so it's sort of an interesting dilemma. But yeah, I could take more rocks, but maybe not for a while. I'll see how the summer goes. I love it.
For those of you who want to get PDUs for this, I'm putting the exit survey link in the chat now. If you want to get that, you'll need to fill that out.
Bernie.
If anybody's interested and lives near Independence, Oregon, the museum in Independence has a display right now with these rocks, and they have UV light. And there, you switch on UV light, and it shows which ones will fluoresce. And they're from Oregon and all over, but they're identified.
That's fun. By the way, my house is sort of a mini museum. I spent many years in Brazil. I don't know if people knew that. So I came back with lots of rocks and mineral samples and a few other things. But uh, a local school asked me to come and do a geology unit for them a few weeks ago. And I said, I can't even walk. But you're welcome to come here. And so they brought their class here on a field trip. So anyway, now I'm becoming a sort of a field trip location for elementary schools in the area. So anyway, the students who come this summer and the teachers I work with this summer will get to sort of see some of that kind of material too. So
Jerry Allegra has a question. Go ahead and unmute yourself and ask away.
I was just curious about your question that says, if Mount Hood should be where Portland is now, why isn't it? And I don't know that. So I was wondering if you could maybe elaborate on why Mount Hood is not where Portland is.
oh, well, usually when subduction occurs and we have an ocean plate coming in and crashing into like North America, it subducts and builds up volcanoes and so on inland and builds up the continent. And then the next plate comes on, it, in the direction our plates are going, it usually comes in behind that one. And so it adds more continent and keeps adding more and more. So the volcanoes, if these plates dive at the level we think, will melt at a certain point. So the volcano should be inland so far behind it. So the range of volcanoes should be working its way towards the west for the case of Oregon. Well, in the case of Oregon, the western volcanoes, which are the foothills you see going, when you go over the Cascades, those foothills you're going up through, those smaller mountains, that's the old western Cascades. They were more ancient than our high Cascades. And so they would have thought the high Cascades, because we were adding material, would now melt inland and come up 40 miles west of there. But our high Cascades are on the east side. It's just the opposite of what's predicted of a, well, okay, this is hard to explain, but this one brings in mountains, then the next one brings in mountains and they appear over here. The next one brings in mountains, they're over here. Well, for us, here's the Western Cascades. The next one came in and they built up on the other side. Okay? What they think happened is a piece of the old plate actually broke off and went horizontal, so the next plate filled in the space and then didn't dive until a later time. That's the best guess now. Okay? So basically, Mount Hood, if it had done what the scientists thought it should have done, would be sitting right on top of Portland pretty much. But we think the piece of plate ahead of it actually broke off. And that had impact on the whole Western US, as a matter of fact. This is all theoretical, but it's the best guess at the moment, which is, I guess, what science is about.
Yeah, exactly. It's always the best guess.
Apparently there are some problems with the form and I apologize for that. I thought I had it set up and I'm going to figure out what's going on with that. I will be sending a follow-up email likely later tonight or tomorrow. And I will make sure that they work when you get those. And if there's still a problem, you let me know, okay?
Well, by the way, every participant this summer will go home with a piece of mantle rock. So
Ooh.
Oregon is unusual. It's a place where mantle rock was actually thrust up to the surface.
Wow, how cool. And whatever you don't give away this summer, I'm sure we could probably take it down to Eugene.
So Jerry, how big are your samples? Are they
Okay.
big, or are they fist size, or I could hold them in my hand, or?
Well, the student samples will be about like this, not the little tiny ones you get in those things. They'll be about this size. And the display samples will be display samples will be bigger, bigger than that, or things you could have on your desk, conversation pieces, kinds of things like that. So I have traded rocks with mining engineers in Canada. I've traded rocks with people in Alaska. I brought back things from Brazil. I have taken groups on field trips all over Idaho and Oregon and into California, and we've literally come back. My grad students used to come back with sometimes 100 or 150 pounds of rock. Sometimes their trunks were almost scraping the ground as they left our parking lot here.